接下来的场次，我们非常荣幸邀请到演讲嘉宾 Cadence Dr. Paul Cunningham。Dr. Paul Cunningham 将为我们带来题为“以代理 AI 擘画 IC 设计新样貌”的精彩分享。For our next session, it is our great honor to welcome our speaker, Dr. Paul Cunningham, SVP and GM, System Verification Group at Cadence. Dr. Paul Cunningham will share his insights titled Pioneering the Future of IC with Agentic AI. Ladies and gentlemen, please welcome Dr. Paul Cunningham.
Good morning. Last presentation before lunch, so it's okay. So I wanted to begin just to share, I think you probably heard it so many times this week, right? It's just amazing time for the semiconductor industry. Just explosion of custom computing, right? I remember being here last year in Taipei and talking about like $1 trillion for the semiconductor industry, $1.2 trillion. And just in the last 12 months, right, we almost doubled the forecast. And I think, a lot of that, of course, we know is the scale out of compute in the data center, right? This new era of the gigawatt token factory. But I think that observation actually implies, I think even that number can still grow more. If we think about now as we take AI from the data center into the physical world, with autonomous vehicles, with humanoid robots, right? If we underestimated the scale of the data center, how much are we underestimating what can happen as we take AI into the physical world? Now, of course, with great opportunity come great challenges, right? And I think to execute on the roadmaps that are needed, right, to get to this level of scale out, right, we're pushing complexity like we never have before. We're pushing semiconductor geometries down to 14 to 10 angstroms, and we're packing, dozens of dies into a package, side by side on interposers and monolithically stacked in 3 dimensions. And I think easily, right, we're going to be into several trillion transistors in a package by the end of the decade. It's just unbelievable. And then, of course, all that against the backdrop of the need to just relentlessly pull in the schedule. I think we've heard this many times from many of the hyperscalers and the leading foundation model providers, right? If there's a new model in AI coming out every 3 to 6 months, and you're going to take 2 years end to end for a new chip architecture, that's going to mean you're at least 4 generations out of date by the time your AI accelerator is into mass production. So the need and the desire to just shrink the schedules is also like it never has been before. Now, of course, I think that fundamentally that's what Cadence, that's what the EDA industry in general, that's what we've been here to do, right? Since day one, we've been around for almost 40 years, and it's all been about delivering you huge order of magnitudes boost in productivity. Even today, right, to do $100-200 trillion transistor device, you could never do that if you were laying out all of those transistors by hand. And I think actually, if you step back, if you look at kind of how we've done this as an industry over the last 30, 40 years, I think the 2 key themes that have applied actually still apply very well to leveraging AI to actually give us that next leap in productivity that we so desperately need over the coming 2-3 years. So I think the first of these is abstraction, right? So most of the transistors are not actually laid out by hand anymore. We're actually coding in higher description level languages, right? System Verilog, VHDL, and these languages actually are almost as flexible as a typical modern software programming language like Python or C++. And then we're automatically compiling and synthesizing down those final transistor layouts from those high-level descriptions. And if you think to how AI can give us that next leap, right? It is that opportunity to raise the abstraction 1 level further. Right? We can actually begin now with architecture diagram specifications in natural language, and we can actually begin that compilation process automatically from those higher level of descriptions. And then I think the other trend, and it's something that's possibly less often called out, is is reuse, right? There's an enormous amount of replication in semiconductors. And as an industry, right, we've actually made the entire process of design, the way our customers are designing chips and the way our tools are architected under hood, to make them incredibly hierarchical. Anytime anything is replicated or repeated, we don't want to repeat that effort either on your side or on our side in our tooling. And that concept of reuse, again, I think is the other key opportunity to deliver that next leap in productivity, in that with AI, we can take reuse from the design to human tasks. All of that time that engineers are spending day to day, iterating, exploring, debugging, fixing, those kind of things, we now actually have a computational platform in front of us that can actually automate those tasks. So I think this idea of abstraction and reuse, this is what can absolutely give the productivity that we need to take the industry to $2 trillion, 2 trillion transistors and beyond. So how are we doing this? I think, for Cadence, at least three key phases of AI, right? Optimization AI, conversation AI, and agentic AI. And agentic AI, that's really the end state. That's the one that can give us this next leap in abstraction, this new era of automating end-to-end tasks, debugging, fixing, iterating, and so on. And I'll get to that, but I did want to spend a little bit of time on optimization AI and on the conversation AI, because I think they're very important foundational elements, and they're part of the overall journey that we're taking. And certainly at Cadence, we continue to invest heavily here as well. So optimization AI, so this is not LLM based. So this is bespoke custom neural networks that we implement deep inside our tools for specific purposes to achieve better scalability, better performance, better quality of results. And what we lack in terms of the complexity of these models, we gain in terms of the fact that they're very lightweight. So we can actually train them on the fly on your designs real time. They're living, breathing things that can learn about your needs and your capabilities. So like one example of this is what we call our Cerebrus technology. So this has been out for many years in the market, thousands of tape outs. And this is a bespoke neural network that allows you to perform exploration in the digital backend. So you can point Cerebrus at a digital place and route block. You can give it, you say, here's 100 CPUs, here's 1,000 CPUs. Please go off and explore all the many different parameters and settings and strategies to try to close that block in the backend with the best possible power, performance, and area. And as an example of the fact that the investment here continues, it's not like been there, done that, move on. Even more recently now, we've been taking our Cerebrus neural system and looking at how we can scale it to the full SoC level. So now today you can point Cerebrus at an entire SoC with 10, 100 blocks, and you can say, here's 2,000, 5,000, here's 10,000 CPUs. Please go off and explore autonomously how to close all of those blocks as efficiently as possible. And we can take learning from one block and apply that on the fly to another block. We can even take learnings from a previous chip and apply them now to a next generation chip. So I think these bespoke networks are very powerful, and there's still a lot of opportunity for them. Another example in digital verification. So here, the way we find bugs in these hundreds of a billion transistor chips is incredibly randomized. We generate these test harnesses, these test environments that throw pseudo-random stimulus at the devices, and they can consume literally billions of CPU hours trying to explore the state space and catch different corner case bugs. So again here, we can create a bespoke neural system, and I emphasize here actually it turns out to be a very different system. So a different kind of neural network, a different kind of machine learning method that compared to Cerebrus that works very well in verification. And here we can make that whole randomized process dramatically more efficient, 5x, 10x, sometimes 20x less compute to get the same verification quality. And again here, the journey is not done, right? We've now started more recently actually using that machine learning system to try to catch different areas of the state space that have so far been unreached. So we can actually literally find more bugs in your chip. We can actually, what we call close coverage, and complete the verification cycle faster. So I think these custom neural networks, which, in fairness, we've been working on since 2018, 2019, a long, long time, a lot of opportunity. And I think it's very important to remember that AI is not one just thing. And I think even large language models are going to evolve in the future as well. Okay, so now to LLM-based AI. So before we get to that end-to-end agentic autonomy, one of the more basic things that we can do is we can make all of our software products conversational. So the reality is that chip design today, the tools that we are delivering and are being used are themselves very complex. They have very complex scripting and control languages. They have very complex GUIs with many different kinds of visualizations that can allow you to understand and see what's going on in your design. And engineers today, they spend a huge amount of time every day, day in, day out, interacting with our software, analyzing things, exploring things, configuring different visualizations, writing on the fly scripts, mini programs to help them in their tasks. All of that can now become conversational. You can start to just chat with our products. You can, in natural language, ask them what you want to do, and they will automatically go and perform the necessary GUI and scripting operations under the hood. And done right, it can be very, very effective. So you're not so much automating tasks as making the tasks go much faster. So the user is still driving all the tasks, but they can run 10, 100 times more quickly. And we have a lot of successes here, especially when we put them natively into the environments, that context awareness. So as you're interacting with our tools, you can right-click, you can get the tooltips, you can get drop-downs, you can get suggestions to help you without even having to type the prompt, just with a right-click menu, perform that next task. So again here, not revolution, but I think very important on that journey to driving more and more productivity in your day-to-day activities. Okay, so now to these complex agentic tasks, right? What has really transformed the software industry, certainly in the last 6 to 12 months. So actually one of the first things that comes up here and is asked all the time, why Cadence? Why EDA, right? You have agentic solutions from the frontier model providers. Why not just have your existing, your Codex, your Claude Code, your anti-gravity, Gemini CLO? Why not have them just work directly with the core EDA tools? And it's something I've thought about a lot. And I think fundamentally, the reason is the complexity of the task, right? To do agentic chip design, the amount of information that needs to be ingested is vast. Millions and millions of tokens. And the complexity of the task is very, very high. So you can't just throw it all at an LLM and get the response that you want. You really need to create quite a complex flow or a scaffold to divide and conquer the problem, to break it up into a series of steps to, if you like, guardrail the LLM process. And that guardrailing involves a lot of iterating with the grounded tools that we've already built over the last 30 or 40 years. So iterating with classic EDA to analyze, assess, to check, to explore. And then the data that's coming in, that needs to be really organized. So you actually have to create some kind of semantic database, what the academics call more a knowledge graph, right? So organize all the information, understand the relationships at different levels of abstraction, so you can then feed up the right information in the right bite-sized portion for each individual LLM call. And if you actually sort of step back from that and you compare it to, well, what have we done in EDA for the last 30, 40 years? It has all the ingredients of actually being literally an EDA tool. So what we do today in place and route, in synthesis, in simulation, in formal, right? We have very complex flow controls. Again, we divide and conquer the problem under the hood. And we have a number of different algorithms, analysis algorithms, optimization algorithms, and we walk them through in an expert system and iterate them towards converging on the result that you're looking for. So it's a different language, a different terminology in AI. We don't talk about algorithms, we talk about skills, right? We don't talk about flow control, we talk about scaffolding. But I can see already, right, the complexity of an agentic solution is absolutely trending over the next 6, 12, 24 months to be millions of lines of scaffolding and prompt engineering through skills. And the knowledge graphs are getting easily as complex as our core design databases in EDA. So I think, to actually deliver an agentic solution with quality, with predictability that you can trust to design your trillion transistor semiconductor devices, it's not an easy task, right? There are many LLMs out there. We're seeing a lot of in the news recently about the cost and the compute of tokens. So we need to use tokens very efficiently, use the right LLM for the right purpose. So I think the end state is a very heterogeneous system and a very, very complex system. And it's something that actually I do genuinely feel that Cadence and my colleagues here in the EDA industry, we can really deliver what you need to get the productivity that you so desperately deserve. The other point I'd call out, and I think this is a really, really interesting thing, and we've got a lot of people on it now, is if our tools, our core traditional tools, are being driven by agents, they're not being driven by humans, then there's a lot of scope for us to actually change the input-output to our tools. Agents actually can control our tools at a much lower level of granularity than a human, and they can read back in a lot lower level profiling data, insights about what's happening than a human ever could. I mean, one of the constant things for me for the last 20 years is usual customer complaint that we put too much information out of our tools. There's too many lines in our log file. Our profiling reports are too hard to understand. Agents, on the other hand, have no problem with all of this. So I actually see a trend towards a more deeper fusion where we're going to peel back the skin of our core EDA tools, and we're actually going to integrate them at a much lower and fine-grained level with agentic systems of the future. And that's going to be very, very key to enabling additional productivity gains, additional quality of result gains from agentic AI. All right, so let's talk a little bit about going down this path. So, at Cadence, we've announced over the last few months, right, a huge investment, a huge commitment to create broad-based, end-to-end agentic solutions, what we call together our Cadence Agent Stack. So we have solutions for big digital front-end, design and verification, digital back-end, custom and analog design, 3D IC, and multi-physics. So, and we're talking, literally thousands of people across the company, all aligning around these end-to-end agentic capabilities. And then we're offering, a fully unified UI environment. You can access all of the agents combined together with knowledge sharing across them through our Agent Stack UI. So the first one, and the one that I think has had the most attention, has been ChipStack. So ChipStack is for big digital front end, so coding RTL, writing tests, closing coverage, running formal verification. And it's true. I mean, it's been an amazing ride. We've had a lot of support from early adopters. And I think it's a great shout out to the point I was making that there really is something for Cadence and the EDA vendors to bring to the table here in agentic AI, that writing system Verilog, verifying big digital front end probably is the closest thing you can get to software design and software testing in Python and C++. So if we're able to see already deltas and see the kind of traction that we're seeing there, just imagine the kind of delta that we can deliver as we move into more bespoke domains such as digital backend and analog schematic and layout. Now, of course, I'm so grateful to be here, following Jensen earlier, who announced the sort of next level of our collaboration. They've been a great partner for us since the beginning with ChipStack. And we've really now taken this over the last few months to the next level, dramatic improvements in their overall verification productivity. And in particular, showing here, some of the infrastructure scale out and the capabilities that NVIDIA are providing that really help us move faster in agentic AI. So I talked about how our agents need to run all our tools in different ways at different times autonomously. So how do you actually scale that out? How do you actually deploy and run Cadence tools in an agentic framework. And so the NVIDIA OpenShell container provides a really actually nice way to create a normalized layer for agents to scale out on the cloud, different runs, and in your data center, different runs of our tools with security, with efficiency, and with a common framework. And then again, of course, Jensen shared some great data on Nemotron 3 Ultra, and we saw the same actually. So enabling Nemotron with ChipStack, some very good results as well. And so, delighted to be able to actually have Nemotron deploy with ChipStack at NVIDIA. Another, I think, good example actually is what I call our own customer zero. So, we have over 1,000 digital designers in our design IP group, developing standard interfaces, protocols, and so on. And so, of course, they've actually been an amazing early partner for us. And I've got an example here, on our PCIe 7 controller. So this is very complex IP, right? 6,000 page specification. Everyone knows PCIe is a pretty badass protocol. The team rolled out ChipStack, and you can see there, they used it. It's a hierarchical design. We actually have to generate a top level. We have to divide it into different blocks. The size of the IP is so complex. And then build the whole verification environment, test plan, coverage plan, and so on. And you can see there some of the raw stats, what ChipStack was able to do. So it got a lot of the way autonomously. And I think the overall conclusion of the team end-to-end was about a 2x improvement in schedule to get the IP completed front to back. And I'm very confident, I think that 2x is going to go to 10x over the next 6 to 12 months. So that's ChipStack. So as I mentioned, right, we're moving forwards now. So we're into beta with InnerStack. So this is the same approach, but taken into big digital backend. So autonomously focusing on how do you fix congestion violations, routing violations, timing violations, EMIR in the backend. How do you automate the creation of floor plans? Very exciting technology, same concepts as ChipStack. And then again, VeraStack. So here, I mean, this is probably one of the most manual things, one of the least automated things over the last 30, 40 years in our industry. Very complex GUIs, very interactive. How do you create analog schematic layouts? And then how do you actually place and route those layouts into final mask sets? And we are actually really seeing, so same kind of concepts with VeraStack, that we can start to automate those tasks end to end. So InnerStack, VeraStack into early betas, and I'm very much looking forward to some great announcements about the productivity gains to be had there in the coming months. All right, so before I wrap up, I just want to say a little bit actually about some middleware, a platform we have called Jedi. So in this agentic world, where Cadence has all these different super agents and conversational AI, so on, how do we actually enable you to scale that out in an organized fashion in your organizations? And I think that's something we called out actually very early, right? That you need a way to set up, get through InfoSec in controls in your company, and have a framework that allows you to configure which LLMs can we use, both cloud frontier models and on-prem open weight models. And also all that data, all that knowledge graph data I was quite talking about, who is allowed to see what data, right? Different teams in your organization may not be able to see each other's data, again, for security and compliance reasons. So Jedi is our middleware platform. We're actually into our third generation of Jedi now. So it has very streamlined install setup, working through an InfoSec checklist, and it gives you all of that ability to silo your data, to run LDAP authentication, to support both on-prem open weight models and frontier cloud models, and then a lot of telemetry and analytics and everything to help you make sure you can manage the costs of the agentic deployments in your organizations. And to do all of that with a very lightweight overhead. So 20 milliseconds overhead for any request through Jedi, your network. So all Cadence agents work through Jedi, and then Jedi is the thing that connects to your underlying LLM compute and models. So yeah, really exciting times. I think there's this really nice kind of duality, right? That the world is changing. The semiconductor industry is exploding because of AI in the data center, AI in the physical world. But at the same time, we really need to use AI to transform how chips are designed so that we can actually move at the pace that we need to move to execute on those roadmaps needed for the scale out of AI in the data center and the physical world. So thanks so much for your time and enjoy your lunch.